Disjoint sets and union-fine data structure. Welcome to this lecture on disjoint sets and the union-fine data structure. In this lesson, we are going to study one of the most elegant and efficient data structures in computer science, the disjoint set, also known as the union-fine data structure or disjoint set union, often abbreviated as DSU. Although the idea behind this data structure is simple, it has enormous practical importance. Disjoint sets are used in graph algorithms, network connectivity problems, image processing, clustering algorithms, compiler design, and many other areas of computer science. In this lecture, we will understand the concept of disjoint sets, study the union, and find operations, explore their efficient implementations using trees, discuss optimizations such as weighted union and path compression, and finally, see how these ideas are used to solve computer or equivalence relation problems. Let us begin with the basic concept. Suppose we have a finite collection of elements. Let us call this collection the universe. For example, imagine we have 10 elements numbered from 1 to 10. Initially, every element stands alone. That means element 1 belongs to one set. Element 2 belongs to another set. Element 3 belongs to a third set, and so on. At this stage, we have 10 different sets. The important condition is that these sets are disjoint. The word disjoint means that no element belongs to more than one set at the same time. In mathematical terms, if we have two sets, Si and Sj, their intersection must be empty. This means there should be no common elements between them. As operations are performed, these individual sets may merge with each other. For example, if we combine the set containing element 1 with the set containing element 7, then those two sets become a single larger set. Similarly, other sets may merge as well. The data structure that efficiently manages these operations is called the union-fine data structure. It supports two fundamental operations. The first operation is called union. The second operation is called find. Let us understand these one by one. The union operation combines two different sets into a single set. Suppose one set contains the elements 1, 7, and 8. Another set contains the elements 3 and 4. If we perform a union operation on these two sets, they merge and become a larger set containing 1, 3, 4, 7, and 8. After merging, the original two sets no longer exist separately. Instead, we now have one unified set. The second operation is called find. The find operation answers an important question. Given an element, which set does it belong to? To answer this efficiently, every set has a representative element, usually called the root. The find operation returns the representative of the set containing the given element. Suppose find of 4 returns 1, and find of 7 also returns 1. Then we immediately know that 4 and 7 belong to the same set. This ability to determine connectivity quickly makes union find extremely useful. Now, let us discuss how these sets are represented internally. The most efficient representation uses trees. Each set is represented as a rooted tree. Every node stores a pointer to its parent. The root node has no parent. Therefore, the root acts as the representative of the set. Imagine we have 3 sets. The first set contains the elements 1, 7, 8, and 9. The root of this set is 1. Elements 7, 8, and 9 point upward to 1. The second set contains the elements 2, 5, and 10. The root is 2. Elements 5 and 10 point to 2. The third set contains the elements 3, 4, and 6. The root is 3. Elements 4 and 6 point upward to 3. This tree representation allows us to perform union and find operations efficiently. Internally, These trees are usually stored using an array called parent. If parent of I is 0, or a negative value, then I is a root. If parent of I is a positive value p, then p is the parent of I. Initially, when every element is in its own set, all entries in the parent array are 0. This indicates that every element is its own root. Now let us understand the simplest implementation of union. Suppose I and j are roots of two different trees. The simplest strategy is to make one root point to the other. For example, we may simply make parent of I equal to j. This joins the two sets. The implementation is extremely simple. However, simplicity sometimes comes with a cost. Let us see why. Now, consider the find operation. Suppose we want to find the representative of element I. We start at I. If I is not a root, we move to its parent. Again, if the parent is not a root, we move upward. This process continues until we reach a node whose parent is 0 or negative. That node is the root. We return it as the representative of the set. This method works correctly. However, there is a serious problem. If we perform union operations carelessly, the trees may become extremely unbalanced. Imagine the following sequence of operations. First, we perform union of 1 and 2. Next, union of 2 and 3. Then, union of 3 and 4. Then, union of 4 and 5. This process continues. What happens to the tree? Instead of growing like a balanced tree, it becomes a long chain. 1 points to 2, 2 points to 3, 3 points to 4, 4 points to 5, and so on. The final node becomes the root. This structure is called a degenerate tree. In such a tree, if we want to perform find on element 1, we must travel through every node one by one until we reach the root. If there are n nodes, the find operation requires O of n time. This is inefficient. If we perform many such find operations, the total running time can become quadratic. Clearly, we need a better strategy. To solve this problem, computer scientists introduced two important optimizations. The first optimization is weighted union. The second optimization is path compression, also called collapsing find. Let us begin with weighted union. The main idea is very intuitive. Whenever we merge two trees, we compare their sizes. The smaller tree is always attached beneath the larger tree. This simple rule prevents the formation of long chains. Suppose we have one tree containing 5 nodes and another tree containing 2 nodes. Instead of attaching the larger tree below the smaller one, we attach the smaller tree under the larger tree. As a result, the height of the overall tree remains small. To implement this efficiently, the size of the tree is stored inside the root node. Since the root has no parent, its parent field is available. Instead of storing 0, we store the negative size of the tree. For example, if a tree contains 5 nodes, the root stores -5. If another tree contains 2 nodes, its root stores -2. When two trees are merged, we compare these sizes. The smaller tree becomes the child of the larger tree. The size values are updated accordingly. This simple idea has a remarkable effect. A famous theorem proves that if weighted union is always used, then the maximum depth of any node becomes at most logarithmic. In other words, the height of the tree never exceeds approximately log base 2 of n. This means the find operation now requires O of log n time instead of O of n. This is a huge improvement. But computer scientists did not stop here. They discovered an even more powerful optimization called path compression. The idea behind path compression is elegant. Suppose we perform find on a node. To locate the root, we travel upward through several parent pointers. Once the root is found, why should we keep the old path? Why not connect every node directly to the root? That is exactly what path compression does. After the root is discovered, we retrace the path. Every node encountered along the path is updated so that its parent points directly to the root. As a result, future find operations become extremely fast. Imagine a chain of nodes. The root is at the top. Node A points to the root, node B points to A, node C points to B. Now suppose we execute find on node C. Initially, the search path is C to B to A to root. After path compression, C points directly to the root. Similarly, B also points directly to the root. The tree becomes much flatter. Future find operations on B or C require only one step. This optimization dramatically improves performance. In fact, when weighted union and path compression are combined, the resulting algorithm becomes extraordinarily efficient. A famous result, due to Robert Tarjan, proves that the total running time for M find operations and N union operations is proportional to M multiplied by a function called the Inverse Ackermann function. This function is denoted by alpha. The Ackermann function itself grows at an unimaginably fast rate. Its inverse grows unbelievably slowly. For all practical input sizes that can ever occur in computer systems, the value of alpha is less than or equal to 4. This means that the average cost of each operation is practically constant. In other words, union find behaves almost like an O of 1 data structure. This is one of the reasons why union find is considered one of the most efficient data structures ever designed. Now, let us see a practical application. One important use of union find is computing equivalence classes. Suppose we have 5 variables. Initially, each variable belongs to its own set. Now we are told that 1 is equivalent to 2. We perform find on 1. The result is 1. We perform find on 2. The result is 2. Since they belong to different sets, we perform union. Now 1 becomes the representative of a set containing 1 and 2. Next, we are told that 3 is equivalent to 4. Again, we perform union. Now 3 becomes the representative of a set containing 3 and 4. Later, suppose we are told that 1 is equivalent to 3. We perform find on 1 and obtain 1. We perform find on 3 and obtain 3. Since they are different, we perform union. Now the two sets merge. The resulting set contains 1, 2, 3, and 4. The representative becomes 1. Finally, suppose we perform find on 4. The path is 4 to 3 to 1. Using path compression, the parent of 4 is updated directly to 1. Now, 4, 3, and 2 all point directly to 1. The tree becomes flatter. Subsequent find operations become extremely fast. This example illustrates how union find dynamically maintains groups of equivalent elements while providing near constant time operations. Let us summarize this lecture. We began by understanding disjoint sets, where every element belongs to exactly one set and no two sets overlap. We studied the two fundamental operations, union and find. We then explored tree-based implementations and observed the problem of degenerate trees. To overcome this issue, we introduced weighted union, which keeps trees balanced, and path compression, which flattens trees during search operations. Finally, we saw Tarjan's remarkable result, proving that the combination of these optimizations makes union find one of the fastest and most efficient data structures in all of computer science. Because of its elegance, efficiency, and wide range of applications, union find remains a fundamental topic in algorithms and data structures, and it continues to play an important role in modern computing systems. Thank you for listening, and in the next lecture, we will continue exploring more advanced topics in algorithms design and analysis.